Attention is all you need. Abstract. The dominant sequence transduction models are based on complex, recurrent, or convolutional neural networks that include an encoder and a decoder. The best performing model also connects the encoder and decoder through an attention mechanism. We propose a new simple network architecture, the transformer based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. Experiments on two machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. Our model achieves 28.4 BLEU on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles, by over 2 BLEU. On the WMT 2014 English to French translation test, our model establishes a new single model state-of-the-art BLEU score of 41.8 after training for 3.5 days on either 8 GPUs, a small fraction of the training costs of the best models from the literature. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. Introduction. Recurrent neural networks, long short-term memory, 13, and gated recurrent, 7, neural networks in particular have been firmly established as state-of-the-art approaches in sequence modeling and transduction problems such as language modeling and machine translation, 38.2.5. Numerous efforts have since continued to push the boundaries of recurrent language models in an encoder-decoder architecture, references 38.24.15. Recurrent models typically factor computations along the symbol position of the input and output sequences. Aligning the positions to steps in computation time, they generate a sequence of hidden states, hi, as a function of the previous hidden state, hi minus 1, and the input for position I. It says t, I misread that. This inherently sequential nature precludes parallelization within training examples, which becomes critical at longer sequence lengths, as memory constraints limit batching across examples. Recent work has achieved significant improvements in computation efficiency through factorization tricks, ref 21, and conditional computation, ref 32, while also improving model performance in case of the latter. The fundamental constraint of sequential computation, however, remains. Attention mechanisms have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing modeling of dependencies without regard for their distance in the input or output sequences, references 2 and 19. In all but a few cases, refer 27, however, such attention mechanisms are used in conjunction with a recurrent network. In this work, we propose the transformer, a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significant more parallelization and can reach a new state-of-the-art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. 2. Background. The goal of reducing sequential computation also forms the foundation of the extended neural GPU, ref 16, ByteNet, ref 18, and ConvS2S, ref 9, all of which use convolutional neural networks as basic building blocks, computing hidden representation in parallel for all input and output positions. In these models, the number of operations required to relate signals from two arbitrary input or output positions grows in the distance between positions, linearly for ConvS2S and logarithmically for ByteNet. This makes it more difficult to learn dependencies between distant positions, ref 12. In the transformer, this is reduced to a constant number of operations, albeit at the cost of reduced effective resolution due to averaging attention-weighted positions, an effect we counteract with multi-head attention as described in section 3.2. Self-attention, sometimes called intra-attention, is an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence. Self-attention has been used successfully in a variety of tasks, including reading comprehension, abstract summarization, textual entailment, and learning task independent sentence representation, references 4, 27, 28, 22. End-to-end memory networks are based on a recurrent attention mechanism instead of sequence-aligned recurrence and have been shown to perform well on simple language question answering and language modeling tasks, reference 34. To the best of our knowledge, however, the transformer is the first transduction model relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolution. In the following sections, we will describe the transformer, motivate self-attention, discuss its advantages over models such as reference 1718 and reference 9. Model architecture. Most competitive neural sequence transduction models have an encoder-decoder structure, references 5-35. Here the encoder maps an input sequence of symbol representations, x1 to xn, to a sequence of continuous representations, z equals z1 to zn. Given z, the decoder then generates an output sequence, y1 to yn, of symbols one element at a time. At each step the model is autoregressive, reference 10, consuming the previously generated symbols as additional input when generating the text. The transformer follows this overall architecture using stacked self-attention and pointwise, fully connective layers for both the encoder and decoder, shown in the left and right halves of Figure 1 respectively. Showing Figure 1. Reference 3.1, Encoder and Decoder Stacks. Encoder. The encoder is composed of a stack of n equals 6 identical layers. Each layer has two sublayers. The first is a multi-head self-attention mechanism, and the second is a simple position-wise fully connected feed-forward network. We employ a residual connection, ref 11, around each of the two sublayers, followed by layer normalization, reference 1. That is, the output of each sublayer is layer norm x plus sublayer x, where sublayer x is the function implemented by the sublayer itself. To facilitate these residual connections, all sublayers in the model, as well as the embedding layers, produce outputs of dimension d model equals 512. Decoder. The decoder is also composed of a stack of n equals 6 identical layers. In addition to the two sublayers in each encoder layer, the decoder inserts a third sublayer which performs multi-head attention over the output of the encoder stack. Similar to the encoder, we employ residual connections around each of the sublayers, followed by layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I. 3.2. Attention. An attention function can be described as mapping a query and a set of key value pairs to an output, where the query, keys, values, and output are all vectors. The output is computed as a weighted sum of the values, where the weight assigned each value is computed by a compatibility function of the query with the corresponding key. Figure 2, left scaled dot product. Attention, right, multi-head attention consists of several attention layers running in parallel. 3.2.1. Scaled dot product attention. We call our particular attention scaled dot product attention, figure 2. The input consists of queries and keys of dimension dk and values of dimension dv. We compute the dot product of the queries with all keys, divide each by the square root of dk, and apply a softmax function to obtain the weights of the values. In practice, we compute the attention function on a set of queries simultaneously, packed together into a matrix Q. The keys and values are also packed together into matrices K and V. We compute the matrix of outputs as attention QKV equals softmax QK to the power of T over square root of DK times V. The two most commonly used attention functions are additive attention, reference 2, and dot product, multiplicative attention. Dot product attention is identical to our algorithm, except for the scaling factor of 1 over square root of dk. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer. While the two are similar in theoretical complexity, dot product attention is much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. While for small values of decay the two mechanisms perform similarly, additive attention outperforms dot product attention without scaling for larger values of decay, reference 3. We suspect that for large values of decay, the dot products grow large in magnitude, pushing the softmax function into regions where it has extremely small gradients, reference 4, or footnote 4. To counteract this effect, we scale the dot products by 1 over square root of dk. Footnote 4. To illustrate why the dot products get large, assume the components of q and k are independent random variables with mean 0 and variance 1. Then their dot product q times k equals the sum of all qk from I equals 1 to dk has mean 0 and variance dk. 3.2.2 Multi-head attention. Instead of performing a single attention function with d-model dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values h times with different learned linear projections to dk, lowercase k, and dv dimensions, respectively. On each of these projected versions of queries, keys, and values, we then perform the attention function in parallel, yielding dv dimensional output values. These are concatenated and once again projected, resulting in the final values as depicted in Figure 2. Multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. With a single attention head, averaging inhibits this. Multi-head QKV equals concatenated head 1 to head h times w to the power of o, where head I equals attention QWI to the power of k, QWI to the power of q, VWI to the power of v, where the projections are parameter matrices, WI to the power of q for the set of R d-model cross product dk, W sub I to the power of k for the set of R d-model cross product dk, Wi to the power of v for the sub of R d-model cross product d sub v, and W supra O for the set of R HDV cross product d model. In this work, we employ H equals 8 parallel attention layers or heads. For each of these, we use dk equals dv equals d model over H equals 64. Due to the reduced dimension of each head, the total computational cost is similar to that of single head attention with full dimensionality. 3.2.3 Applications of attention in our model. The transformer uses multi-head attention in 3 different ways. In encoder-decoder attention layers, the queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanisms in sequence-to-sequence models such as Ref 38.2.9. The encoder contains self-attention layers. In a self-attention layer of all the keys, values, and queries come from the same place. In this case, the output of the previous layer in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. Similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. We implement this inside of a scaled dot product attention by masking out, setting to negative infinity, all values in the input of the softmax which correspond to illegal connections. See Figure 2. 3.3 Position-wise feed-forward networks. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. This consists of 2 linear transformations, with an R, sorry, with a RELU activation in between. FFN of x equals max bracket 0 xw1 plus b1 close bracket times w2 plus b2. While the linear transformations are the same across different positions, they use different parameters from layer to layer. Another way of describing this is as two convolutions with kernel size 1. The dimensionality of input and output is d model equals 512, and the inner layer has dimensionality dff equals 2048. Embedding and softmax. Similarly to other sequence transduction models, we use learned embedding to convert the input tokens and output tokens to vectors of dimension d model. We also use the usual learned linear transformation and softmax function to convert the decoder output to predict next token probabilities. In our models, we share the same weight matrix between the two embedding layers and the pre-softmax linear transformation, similar to Ref 30. In the embedding layers, we multiply those weights by square root of d model. 3.5 Positional encoding. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the token in the sequence. To this end, we add positional encodings to the input embeddings at the bottoms of the encoder and decoder stacks. The position encodings have the same dimension, d model, as the embeddings, so the two can be summed. There are many choices of positional encodings learned and fixed, reference 9. And we have table 1, maximum path lengths per layer complexity and minimum number of sequential operations for different layer types. N is the sequent length, D is the represented dimension, K is the kernel size of convolutions, and R the size of the neighborhood and restricted self-attention. So we have a 4-column chart. Layer type is self-attention, recurrent, convolutional, and self-attention restricted. Complexity per layer is O n squared dot D, O n dot D squared, O k dot n dot D squared, O r dot n dot D. Sequential operations are O1, On, O1, and O1, and maximum path lengths equals O1, On, O log k of n, and On over r. In this work, we use sine and cosine functions of different frequencies. Pe, positive 2i, equals sine of pos over 10,000 to the power of 2i over d model, and Pe pos 2i plus 1 equals cosine of pos over 10,000 to the power of 2i over d model, where pos is the position and I is the dimension. That is, each dimension of the positional encoding corresponds to a sinusoid. The wavelengths form a geometrical progression from 2 pi to 10,000 times 2 pi. We choose this function because we hypothesized it would allow the model to easily learn to attend by relative positions, since for any fixed offset k, Pe positive plus k can be represented as a linear function of Pe positive. We also experimented using learned positional embeddings, reference 9, instead, and found that the two versions produce nearly identical results, table 3, row E. We chose the sinusoidal version because it may allow the model to extrapolate to sequence length longer than the ones encountered during training. 4. Why self-attention? In this section, we compare various aspects of self-attention layers to the recurrent and convolutional layers commonly used for mapping one variable length sequence of symbol representations, x1 to xn, to another sequence of equal length, z1 to zn, with xi, zi for the set of r to the d, such as a hidden layer in typical sequence transduction encoder or decoder. Motivating our use of self-attention, we consider 3 desiderata. One is the total computational complexity per layer. Another is the amount of computation that can be parallelized as measured by the minimum number of sequence operations required. The third is the path length between long-range dependencies in the network. Learning long-range dependencies is a key challenge in many sequence transduction tasks. One key factor affecting the ability to learn such dependence is the length of the path forward and backward signals have to traverse in the network. The shorter these paths between any combination of positions in the input and output sequences, the easier it is to learn long-range dependencies, reference 12. Hence, we also compare the maximum path length between any two input and output positions in network composed of the different layer types. As noted in Table 1, a self-attention layer connects all positions with a constant number of sequentially executed operations, whereas a recurrent layer requires O times n sequential operations. In terms of computational complexity, self-attention layers are faster than recurrent layers when the sequence length n is smaller than the represented dimensionality d, which is most often the case with sentence representation used by state-of-the-art models in machine translations, such as word piece, Ref 38, and byte pair, Ref 31 representations. To improve computational performance for tasks involving very long sequences, self-attention could be restricted to considering only a neighborhood of size r in the input sequence centered around the respective output position. This would increase the maximum path length to O n over r. We plan to investigate this approach further in further work. A single convolutional layer with kernel width k less than n does not connect all pairs of input and output positions. Doing so requires a stack of O n over k convolutional layers in the case of contiguous kernels, or O log k of n log n base k in the case of dilated convolutions, Ref 18, increasing the length of the longest paths between any two positions of the network. Convolutional layers are generally more expensive than recurring layers by a factor of k. Separable convolutions, Ref 6, however, decreases the complexity considerably to O k.n.d plus n.d squared. Even with k equals n, however, the complexity of a separable convolution is equal to the combination of a self-attention layer and a pointwise feed-forward layer to the approach we take in our model. As side benefits, self-attention could yield more interpretable models. We inspect attention distributions from our model and present and discuss examples in the appendix. Not only do individual attention heads clearly learn to perform different tasks, many appear to exhibit behavior related to the syntactic and semantic structure of the sentences. 5. Training. This section describes the training regime for our models. 5.1 Training data and batching. We trained on the standard WMT 2014 English-German dataset consisting of about 4.5 million sentence pairs. Sentences were encoded using byte pair encoding, reference 3, which has shared source target vocabulary of about 37,000 tokens. For English-French, we used the significantly larger WMT 2014 English-French dataset consisting of 36 million sentences and split tokens into 32,000 word piece vocabularies, reference 38. Sentence pairs were batched together by approximate sentence length. Each training batch contains a set of sentence pairs containing approximately 2,500 source tokens and 2,500 target tokens. Reference 5.2 Hardware and Schedule. We trained our model on one machine with 8 NVIDIA P100 GPUs. For our base models used the hyperparameters described throughout the paper. Each training step took 0.4 seconds. We trained the model base for a total of 100,000 steps, or 12 hours. For our big models, described on the bottom line of Table 3, step time was 1.0 seconds. The big models were trained for 300,000 steps, 3.5 days. 5.3 Optimizer. We used the Atom Optimizer, reference 20, with beta 1 equals 0.9, beta 2 equals 0.98, and epsilon equals 10 to the power of 9. We varied the learning rate over the course of training according to the formula. L rate equals d, the power of negative 5 submodel, dot min, bracket, step num to the power of negative 0.5, step num dot warm up steps to the power of negative 1.5. This corresponds to increasing the learning rate linearly for the first warm-up training steps, and decreasing it thereafter proportionally to the inverse square root of the step number. We used warm-up steps equals 400,000. Regularization. We employ three types of regularization during training. Residual output. We applied dropout, reference 33, to the output of each sublayer before it is added to the sublayer's input and normalized. In addition, we apply dropout to the sum of the embedding and the positional encoding in both the encoder and decoder stacks. For the base model, we use a rate of p drop equals 0.1. Table 2. The transformer achieves better BLEU scores than previous state-of-the-art models on the English to German and English to French News Test 2014 test at a fraction of the training cost. And we've got a table with the model, BLEU, and the training cost, and then various competing standards and significantly less training time for the scores are comparable, though they are better than all the competing ones. Label smoothing. During training, we employed label smoothing of value epsilon is equals 0.1, reference 36. This hurts perplexity as the model learns to be more unsure, but improves accuracy and BLEU score. 6. Results. 6.1 Machine Translation. On the WMT 2014 English to German translation task, the big transformer model, transformer big in Table 2, outperforms the best previously reported models, including ensembles, by more than 2.0 BLEU, establishing a new state-of-the-art BLEU score of 28.4. The configuration of this model is listed in the bottom of Table 3. Training took 3.5 days on SP100 GPUs. Even our base model surpasses all previously published models and ensembles at a fraction of the training cost of any of the competitive models. On the WMT 2014 English to French translation task, our big model achieves a BLEU score of 41.0, outperforming all of the previously published single models at less than 1/4 the training cost of the previous state-of-the-art model. The transformer big model trained for English to French used dropout rate p drop equals 0.1 instead of 0.3. For the base model, we used a single model obtained by averaging the last 5 checkpoints, which were written at 10-minute intervals. For the big models, we averaged the last 20 checkpoints. We used beam search with a beam size of 4 and length penalty alpha equals 0.6, reference 38. These hyperparameters were chosen after experimentation on the development set. We set the maximum output left during inference to input length plus 50, but terminated early when possible. Table 2 summarizes our results and compare our translation quality and training cost to other model architecture from the literature. We estimate the number of floating point operations used to train a model by multiplying the training time, the number of GPUs used, and the estimate of the sustained single precision floating point capacity of each GPU. 6.2 Model Variations. To evaluate the importance of different components of the transformer, we varied our base model in different ways, measuring the change in the performance of English to German translation on the development set, News Test 2013. We used beam search as described in the previous section, but no checkpoint averaging. We present these results in Table 3. In Table 3, rows A, we vary the number of attention heads and attention key and value dimensions, keeping the amount of computation constant as described in section 3.2.2. While single head attention has 0.9 BLEU worse than the best setting, quality also drops off with too many heads. Table 3. Variations on the transformer architecture. Unlisted values are identical to those of the base model. All metrics are on the English to German translation development set, News Test 2013. Listed perplexities are per word piece according to our byte pair encoding and should not be compared to per word perplexities. So we have a chart showing the various bases and changes in the variations, I guess. So we've got N, D model, DFF, H, DK, DV, P drop, ELS, train steps, PPL, BLEU, and the number of parameters. So they varied it a bit to um, verify they had the best settings. Table 4, the transformer generalizes well to English constituency parsing. Results are on section 23 of WSJ. So there's parser, training type WSJ 23F1. In table 3, rows B, we observe that reducing the attention key size dk hurts model quality. This suggests that determining compatibility is not easy, and a more sophisticated compatibility function than dot product may be beneficial. We further observe in rows C and D that, as expected, bigger models are better, and dropout is very helpful in avoiding overfitting. In row E, we replace our sinusoidal encoding with learned positional embeddings and observe nearly identical results to the base model. 6.3 English constituency parsing. To evaluate if the transformer can generalize to other tasks, we perform experiments on English constituency parsing. This task presents specific challenges. The output is subject to strong structural constraints and is significantly longer than the input. Furthermore, RNN sequence-to-sequence models may not have been able to train state-of-the-art results in small data regimes. We trained a 4-layer transformer with D model equals 1024 on the Wall Street Journal WSJ portion of the Penn tree bank, reference 25, about 40,000 training sentences. We also trained it in a semi-supervised setting using the larger high confidence and Berkeley parser corpora with approximately 17 million sentences, reference 37. We used a vocabulary of 16,000 tokens from the Wall Street Journal only setting and a vocabulary of 32,000 tokens for the semi-supervised setting. We performed only a small number of experiments to select the dropout, both attention and residual section, reference section 5.4. Learning rates and beam size on the section 22 development set. All other parameters remained unchanged from the English to German-based translation model. During reference, we increased the maximum output length to estimate length plus 300. We used a beam size of 21 and alpha equals 0.3 for both WSJ only and the semi-supervised setting. Our results in Table 4 show that despite the lack of task-specific tuning, our model performs surprisingly well, yielding better results than all previously reported models with the exception of the recurring neural network grammar, reference 8. In contrast to RNN sequence-to-sequence models, reference 37, the transformer outperforms the Berkeley parser, reference 29, even when training only on the WSJ training set of 40,000 sentences. 7. Conclusion. In this work, we presented the transformer, the first sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architecture with multi-headed self-attention. For translation tasks, the transformer can be trained significantly faster than the architectures based on recurrent or convolutional layers. On both WMT 2014 English to German and WMT 2014 English to French translation tasks, we achieve a new state-of-the-art. In the former tests, our best model outperforms even all previously reported ensembles. We are excited about the future of attention-based model and plan to apply them to other tasks. We plan to extend the transformer to problems involving input and output modalities other than text, to investigate local restricted attention mechanisms to effectively handle large inputs and outputs such as images, audio, and video. Making generation less sequential is another research goal of ours. The code we use to train and evaluate our models is available at https://github.com/tensorflow/tensor2tensor. Acknowledgement. We are grateful to Nal Keshbringer and Stefan Goles for their fruitful comments, corrections, and inspiration. And from there, it's references.